All right, let's dive right in. Welcome back to the Explainer. Today, we are setting up the absolute ultimate showdown between the big three elementary sorting algorithms. Now, if you've ever studied computer science, you already know them well. But today, we're not just looking at the textbook theory. We're actually putting them in the ring to find out which one survives the brutal, real-world demands of modern software engineering.
So think about it for a second. Which elementary sorting algorithm actually powers the modern web? It's kind of a provocative question, right? We constantly hear about all this complex, advanced math and highly recursive data structures. But behind the scenes, a seemingly basic algorithm is secretly running the internet. And by the end of this explainer, the answer to that question might completely change how you view fundamental computer science.
Here's our fight card for today's Explainer. 1. Meet the contenders. 2. Mechanics of the ring. 3. The tail of the tape. 4. Stability and swap costs. And finally, 5. The real-world champion.
Round 1. Meet the contenders.
These three algorithms actually have really distinct personalities. In the first corner, we've got bubble sort, the master of the shuffle. It likes to keep things simple, constantly comparing adjacent values and just swapping them if they're out of order. In the second corner, selection sort, the methodical searcher. It takes its sweet time, searching the entire unsorted partition to find the absolute minimum before making even a single swap. And in the final corner, insertion sort, the stable strategist. It methodically builds a perfectly sorted subarray element by element.
Moving right along. Round 2. Mechanics of the ring.
This brilliantly illustrates exactly how insertion sort operates. The array is literally split right down the middle into a sorted region on the left and an unsorted region on the right. The algorithm repeatedly picks the lowest index element of the unsorted region, marked right here by the X, and drags it over, inserting it into its exact, proper position in the sorted region. It's just a continuous, methodical expansion of order.
So how does it actually execute this? Well, it's a clean 1, 2, 3, 4 process. It picks the first unsorted element, the key, then it compares that key backward through the already sorted partition. But notice step 3 here. It shifts larger elements to the right. It doesn't do a full, heavy swap every single time. It just slides the bigger numbers over, creating a little vacancy, and finally drops the key right into that empty slot. It's incredibly efficient with its movements.
All right, round 3, the tail of the tape.
Let's look at the hard numbers. All three of these algorithms hit a massive O of n squared wall in the average and worst cases. Basically, as the dataset grows, the time it takes to sort grows exponentially. But look closely at that best case column. If an array is already sorted, bubble and insertion sort breeze through it in linear, O of n time. Selection sort, on the other hand, totally fails to adapt. Even if the data is absolutely perfect, it blindly searches the whole array, wasting time with an O of n squared best case.
Now, to truly grasp why these algorithms hit that O of n squared wall, we really have to understand this core concept, the inversion. An inversion is simply an ordered pair of indices where the first element is strictly greater than the second element. Essentially, it's just any pair of numbers that are out of order relative to each other. And here's the kicker. Every single time a simple sorting algorithm swaps adjacent elements, it is removing exactly one inversion. Just one.
And that brings us to this harsh mathematical reality. N times n minus 1 all over 4. This formula represents the average number of inversions in any random array. Because these elementary algorithms, like bubble and insertion sort, only resolve one single inversion per adjacent swap, they are forced to do an agonizing amount of work. If you have a massive database, that sheer number of required swaps is exactly why the average case bogs right down to quadratic time.
Okay, round 4, stability and swap costs.
Let's put selection sort and bubble sort head-to-head for a second. Selection sort is unstable, which means if you have two identical values, their original order might actually get jumbled up during a long-distance swap. But it's actually fantastic for flash memory because it minimizes physical writes to the hardware, capping out at a maximum of O of n swaps. Bubble sort, conversely, is perfectly stable, but it wastes a massive amount of energy constantly swapping adjacent elements over and over again just to move a number across the array.
But here is insertion sort's absolute hidden superpower. It is highly adaptive. Think about it. In the real world, data is rarely completely random, right? Think about a server log or a database that just had a few new entries appended to the end. It's usually almost entirely sorted already. Because insertion sort simply stops comparing once it finds the key's proper spot, it literally races through partially sorted datasets in near linear time. It adapts to the data.
And finally, Round 5. The real-world champion.
This adaptability actually builds into something incredible. Insertion sort is so efficient that it evolved into an advanced algorithm known as shell sort. Instead of just shifting elements one tiny spot at a time, it uses what we call gap sequences to literally leapfrog elements across the array. By running insertion sort on these interleaved varying gap sizes, it resolves multiple inversions at once, massively speeding up the whole process before doing one final tight insertion pass.
So who actually takes the crown? Well, plot twist, insertion sort is secretly powering the modern web. The default sorting engine in Python and Java is timsort. In C++, it's intrasort. And both of those are hybrid algorithms built directly on top of insertion sort. Furthermore, massive hardware companies like Cisco use insertion sort inside their network routers because it requires virtually zero extra memory overhead. That prevents catastrophic stack overflows in their embedded systems. It's a real game changer.
And this brings us to the true genius of modern software engineering, the threshold fallback. Look, advanced, lightning-fast algorithms like quicksort or merge sort are absolutely amazing for massive data, but they have really heavy recursive overhead. So what do? When they break a massive array down into smaller partitions of about 20 to 47 elements, they purposely downgrade to insertion sort. For small data sets, insertion sort is mathematically faster and lighter than the most complex algorithms on the planet.
Now, while insertion sort reigns supreme behind the scenes, where does that leave our old friend bubble sort? Well, computer science legend Donald Knuth delivered this absolute knockout blow in his seminal work. He said, "The bubble sort seems to have nothing to recommend it, except a catchy name and the fact that it leads to some interesting theoretical problems. I mean, ouch. In professional software development, bubble sort is entirely obsolete."
Which leaves us with one final, pretty provocative thought to wrap up this explainer. If insertion sort is the secret, highly adaptive engine actually powering our modern languages and hardware routers, and bubble sort is universally recognized as just terribly inefficient, is it finally time to retire bubble sort from computer science education forever? I mean, should we just stop teaching it entirely? It's a fascinating debate about nostalgia versus practical engineering. Anyway, thank you so much for joining me on The Explainer today. Keep learning, keep questioning, and I'll catch you on the next one.